So, can you prove you'll be a good person in exactly 5 seconds? It's a really fascinating question, right? Think about it. Cryptography is absolutely incredible at proving exactly who an AI agent is at T0. You get a signature, a handshake, and boom, the math is airtight. But here's the catch. There is literally no software in the world that can guarantee that same agent will still be acting in its assigned role 5 seconds later. You know who they are at the door, but you have zero mathematical proof of their actual conduct after they walk through it. Welcome to this explainer. Today, targeting a future timeline of 2026-6-6, we're going to embark on an adversarial walkthrough of something truly groundbreaking. We're looking at the On-Chip PMU V0. We're essentially conducting a self-administered technical due diligence, looking specifically at how we can achieve true, verifiable role continuity. And the core philosophy here? Don't trust me? Recompute the receipt. Every single claim we discuss today ships with the exact command you need to recompute it. We aren't relying on theoretical models. We're going to prove everything using bare metal math, physical constraints, and hard numbers measured directly from the silicon. Here is our roadmap for the technical audit. We'll start with the hardware verification gap, move into how this is proven from the metal, explore the unforgeable hardware witness, look at IFIM, where access equals competence, and finally, wrap up with the zero latency economy. Let's dive in. Part 1, the hardware verification gap. We need to talk about the T+5 problem and Rice's theorem. Right now, the entire tech industry is completely obsessed with using software to babysit other software. We're building endless layers of guardrails and monitors. But way back in 1953, Rice's theorem proved that all non-trivial semantic properties of programs are fundamentally undecidable. You just cannot write a program to reliably decide what another program means or what it's going to do. So a software monitor watching an AI model shares its exact failure domain. To put it simply, trying to fix this hardware gap with software wrappers is like a thermometer trying to measure its own fever. It's a mathematical dead end. So how do we get out of this trap? Well, we have to drop underneath the software entirely. We have to go down to the physical geometry of the hardware itself. This brings us to the unity principle, S equals P equals H. Semantic identity maps directly to the physical geometry of the cache line. In this system, simply reaching for a coordinate is the verification that the coordinate matches the map. The software watcher is completely gone. The physical cache hardware itself is doing the verification. Moving on to section 2, proven from the metal. Let's get into the actual due diligence walkthrough. 0.537 nanoseconds. Seriously, let that number sink in for a second. To put that into perspective, light itself barely travels 6 inches in that amount of time. This is the stark, measured speed of the ballistic gate per comparison on commodity ARM64 silicon. On the chip, a 64-bit lane is literally 1 XOR and 1 neon pop count tree. This gate is a combinational circuit. It entirely avoids Turing-complete loops, meaning it gives us a definitive verdict in a fraction of a nanosecond, totally free from any software auditing latency. And if you look at the raw code here, this actual ARM64 disassembly proves total honesty about the architecture. An auditor running OTool on this binary would see exactly this. We aren't faking some magical single instruction scalar CNT here, because honestly, there are 0 of those in the whole binary. On this specific chip, it's not one instruction. It lowers to an XOR, the EOR command, then an fmove, followed by a neon sequence of CNT.8b and an addv.8b for the horizontal add. The exact physical layout on the chip is what's driving the 0.5378 nanosecond verification. Now, you might be thinking, hey, why not just use AVX5112 or those super wide neon vector units to go even faster? Totally fair question. But spinning up those wide vector units from a cold start introduces latency that completely destroys the speed of the very first comparisons, the exact ones that govern a crucial Holtz decision. On top of that, sticking to a 64-bit lane perfectly mirrors the planned hardware tape-out of replicated pop count trees. If you want to scale this thing up, you don't build more complex logic, you literally just print more physical lanes. All right, section 3, the unforgeable hardware witness. Let's take a look at time and the pointer chase. 80 times x. This isn't just a minor speed bump. This is a massive mispenalty between the L1 cache and the main DRAM. You see, time itself is the actual substrate the witness lives in. This 80 times penalty reveals something absolutely incredible. The hardware transit time acts as an unforgeable, unhackable witness. You cannot fake this time delay without literally faking the physical hardware itself. There's just no way. So how exactly do we capture this time as witness? Well, we use a dependent load pointer chase over a random permutation cycle, specifically a single non-overlapping Fisher-Yates cycle. Because there's no predictable stride for the CPU to chase ahead, its prefetcher is completely defeated. The dependency chain forces the out-of-order engine to completely stall because it has to wait for the real physical transit time. And that gives us our unforgeable fingerprint, 1.85 nanoseconds in the L1 cache versus a glaring 148.32 nanoseconds out in the DRAM. Which brings us to the next undeniable metric, 6.51 million walks per second. And the best part? That is entirely L1 resident. It is incredibly stable, operating well above a 3.4 sigma floor across the test harness with a massive aggregate of 600 sigma. It never even touches the slow DRAM. So you're probably wondering how on earth we maintain 6.51 million fan-out walks a second without choking the memory. Simple. We drop the global visited set. Having a global visited set requires constant allocation, which completely blows out the L1 cache. Instead, we use a depth-decayed additive weight to bound the recursion. Because we do that, our working set remains this tiny, static 1152-byte buffer nestled safely inside the L1 data cache. Zero DRAM tax. This whole process powers the sensor, and it operates in 4 distinct steps. First, it ingests the raw bytes. Second, it compresses those semantics into an exact 64-bit physical shape. This essentially burns the text payload away, leaving only its geometry behind, so absolutely nothing sensitive leaks out. Third, it understands by matching that shape to a physical anchor, using our 0.5378 nanosecond gate. And finally, it diffuses that hit across the lattice. The payload is gone, sure, but the exact physical receipt is completely secured. Section 4, IAMF, Access is Competence. And the subtitle says it all. Drifting out of role is revocation. This is where the paradigm completely shifts. Think about legacy identity and access management. Things like RBAC or OAuth. They rely on static tokens. Those can easily be stolen, and verifying them relies on software policy lookups, which dumps us right back into the Rice's theorem trap. IAM-FIM, on the other hand, relies purely on physical position. A permission check isn't a software lookup anymore. It is a hardware-enforced cache hit or miss, and it happens at zero latency. I absolutely love this quote. It captures the crucial point perfectly. The credential is not a token you hold. It is a position you occupy. A role-to-resource match is literally the exact same operation as a competence match. So if an AI agent drifts out of its specific competence lane, boom, it triggers an automatic cache miss. That drift is instant, automatic revocation. There is no stale token left behind for an attacker to steal. Now, you're probably hearing a lot about zero-knowledge proofs, or ZKPs, in this space lately. And don't get me wrong, they aren't fantastic for batch, privacy-preserving compliance. But we deliberately keep ZKPs completely off the hot path. Proving latency actively fights our zero-latency thesis on a per-transaction basis. You just cannot stick a ZKP on a 0.5378 nanosecond gate without slowing it down. They belong on the outer layer, not in the hardware core. Finally, Section 5. The zero-latency economy and the economics of trust debt. Just look at this massive gap in the market today. Over on the left, we've got a highly defensible $760,000 safe note floor per contract, a number so incredibly conservative it survives any technical due diligence. But the real target, that's the middle bar, a $152 million enterprise trust debt exposure. Enterprises are carrying massive, completely unpriced liability right now because they cannot mathematically trust their agents. All while tens of billions of dollars in CapEx are being poured into making those agents faster, totally ignoring the latency of trust. Stepping back, here is what the timeline of the new economy actually looks like. At T0, cryptography proves an agent's identity at the door. Simple. But by T+5, the hardware PMU natively asserts role continuity, proving the agent's intent without a single software audit. When you eliminate the transaction cost of constantly auditing agents in the cloud, you unlock something amazing. Zero-latency machine-to-machine markets where specialized labor and compute can clear at the literal speed of light. So I'm going to leave you with one final, kind of provocative thought. As we look at this trillion-dollar AI industry, you really have to ask yourself, is your agentic infrastructure built on a rock-solid mathematical floor, or is it just a thermometer desperately trying to measure its own fever? Because I'll tell you right now, the future of autonomous agents isn't going to be governed by more software wrappers. It's going to be governed by physical geometry and undeniable hardware receipts that you can recompute yourself. Thanks so much for joining me on this explainer.